Let's look at the following example. I have two discrete random variables, x and y, and the table gives me the joint probability mass function. Remember, expected value of y conditionally on x is a random variable. To figure out exactly what this random variable is, we simply loop over all possible values of x. For x equal to 0, we see that the expected value of y given x equal to 0 is 0.2. And for x equal to 1, we see that the expected value of y conditionally on x equal to 1 is 0.8. So the expected value of y given x, which we can rename to a new symbol, let's say z, it has a probability mass function where the probability that it takes 0.2 is 50%. That's the probability that x is equal to 0. And the probability that it takes 0.8 is 50% as well. The unconditional expected value of y is easily calculated to 0.5. So here is an interesting thing. If I calculate the expected value of my z, that is, if I calculate the expected value of this random variable ey given x, that comes out to be, well, z takes the value 0.2 with the probability of 0.5, and it takes the value 0.8 with the probability 0.5. And that is precisely equal to 0.5. Turns out that this is not a coincidence. The unconditional expectation of y will always be equal to the expected value of the conditional expectation of y given x. This very important result is called the law of iterated expectations. Let's do an example with continuous random variables just to check that it holds for such a case as well. Here I have two continuous random variables with a joint PDF, the range of x, range of y. To find the conditional expectation of y given x, we simply calculate the expected value of y given x equal to lowercase x as the integral y times the conditional density of y given x. If you calculate that integral, it comes out to be 3x plus 2 over 6x plus 3. Then in the final step, you just replace lowercase x with uppercase x, and this random variable is the same then as this one. The random variable z will have a range which goes from 5 over 9 to 2 over 3. We can see that by just plugging in the range of x into this g function here. So to find the expected value of z, we do the integral of z multiplied by the PDF of z. And this part here will be the PDF of z. So the expected value of the conditional expectation comes out to be 7 over 12. If I do the unconditional expectation of y, then I just integrate from 0 to 1 y times the marginal density of y, and that will give me 7 over 12 as well. The reason for this result being so important is that in many cases this expectation is very hard to calculate, while the conditional expectation is very simple. When this is the case, we will use the law of iterated expectations to find the unconditional expectation of y. In these examples, of course, the unconditional expectation was much simpler, but we simply use these examples to show that this result holds. Let's look at the proof of the law of iterated expectations. It's not a particularly important proof, it's just a nice exercise demonstrating how to manipulate various distributions. So let's do the proof for the continuous case. Doing it in the discrete case is very similar, we just use sums instead of integrals. So let's prove that the expected value of ey given x is the unconditional expected value of y. Our notation here is that g of x is the expected value of y given x equal to lowercase x, and g of x is the random variable y given x. What we have here on the left hand side is simply the expected value of g of x. We have a general formula for figuring out the expected value of a function of a random variable. And it goes like this. We integrate x from minus infinity to infinity. We do g of lowercase x, and we multiply that by the PDF of x dx. Before we substitute this for g of x in our integral, let's write this as an integral itself. This we know is the integral over all possible values of y. Y times fy conditionally on x, yx dy. This is my g of x function, so I need to put that in here, replacing the g of x. Let's see what we get then. The expected value of e y given x, or expected value of g of x, integral x equal minus infinity to infinity. Now put g of x in there. We have y equal minus infinity to infinity. Y times fy conditionally on x, yx. Then we have this one, fx of x. We have the dy and the dx. A lot of things will simplify here. The conditional density is given by the joint density over the marginal of x. So if I do this fx of x will cancel with this one. So this whole thing is just equal to the joint PDF. The whole thing is then equal to integral over x minus infinity to infinity, or whatever the range is of x, integral over y times f of x comma y dy dx. If the PDF is well behaved, then I can switch these integrals around. So I can write this as the integral over y, the integral over x. For the integral of x, I can take the y outside. That's a constant in this integral. And then I'm just left with the joint dx dy. We recognize this. If I integrate the joint PDF over all possible values of x, it becomes the marginal of y. So the whole thing is the integral y times fy of y dy, which is indeed the expected value of y. And we've seen that these must be equal. Like I said, not that important, just a nice opportunity for you to practice working with density functions.